everyone, welcome to part 2 of chapter 18. Today we are going to pick up where we left off last time in talking about entropy. The last lecture discussed the first and second laws of thermodynamics, and then we ended by talking about this new concept, entropy, which is kind of a measure of the disorder of things. So now we are going to look at changes in entropy. So what was the entropy before and after a particular change? Maybe it was a reaction, maybe it was a phase change. And then finally, we're going to end up at the third law of thermodynamics, which looks at standard molar entropies. So lots to cover today. Let's get going. So like I said, the focus of this lecture will be on changes in entropy. So that will be delta S. And so the easiest way to look at a change in entropy would be the final minus the initial. So entropy is going to be favorable when the result is a more random system. And we talked about that a little bit last time, right? The entropy of the universe is going to continually increase. So anything that's going to continue to increase the entropy of a system or the entropy of the universe is typically going to be favorable. And this will happen when delta S is positive. So that means that there's a greater entropy in our final state than our initial state. And so here's some examples that increase entropy. So this would be a reaction whose products are in a more random state. So this would be like if we did a reaction and we produced a bunch of gas molecules, and say we had started in a solid, right? Well, gas molecules are more random and more disordered than the solid state. So that would mean that our reaction has increased in entropy. So that would be a favorable change. So solids are going to be our most ordered system, so they're going to have the lowest amount of entropy, and then liquids will have more entropy, and gases will have a lot more entropy than solids or liquids. We can also see a positive change in entropy in reactions that will have a larger number of product molecules than reactant molecules. So maybe our reaction wasn't producing a lot of gas, but maybe it caused our substance to break into more pieces. Well, if we have more pieces, then that will be a more disordered state because we'll have a greater number of microstates. An increase in temperature will also cause more disorder, and I think this follows kind of a logical thought process, right? If we increase our temperature, we're giving our molecules more energy, and therefore they can have more energy to disperse to those microstates, and oftentimes they may change phase, right? They may increase in volume. There's lots of things that go along with an increase in temperature. And then a solid dissociating into ions upon dissolving, that is also going to be an increase in entropy because we had a very ordered crystal structure, right? Like maybe it was sodium chloride and had that alternating pattern of, positive sodiums and negative chlorides. But when it goes into water, all of those ions dissociate and they move about and it becomes much more disordered. So here's some examples of increases in entropy. Again, going from a solid to a liquid. So when our solid melts, we're going to increase our entropy because we have more freedom of motion, right? And our system has more randomness, more disorder. Similarly, if we evaporate a liquid, we are going to increase in entropy, and this is a very large increase in entropy, right? Liquid molecules are still fairly ordered because they're kind of, so close together, and they have strong attractions to each other. They're still going to stay fairly ordered, especially with something like water that's polar, right? We're always going to have that positive hydrogen orienting itself to a negative or, partial negative oxygen. But when they are gas molecules, they don't have to be ordered whatsoever. They just kind of float away and do their own thing. So there's tons and tons of different microstates, so we have a much higher entropy value. And then again, if we are going to dissolve our solid, right? So again, we have this really ordered crystal structure, but when that crystal structure is dissolved and we hydrate our ions, then they are much more disordered. So again, when we have the final condition being more random than the initial condition, that will give us a positive delta S of our system. And delta S of our system, you can also think of that as being delta S of our reaction, because normally our system will be a reaction that we're doing. But the key here is that if we have a positive delta S, then our entropy change is favorable and it's going to be spontaneous. But if we are going to a more ordered system, maybe we are forming a solid, right? Then our delta S of our system is negative, and the entropy change would be unfavorable for this process to be spontaneous. Okay, systems don't typically go and order themselves. There has to be something else happening. So here are our phases of matter. So we have our solid has a very, very low entropy value, right? They are very ordered. And then our liquid is going to be more disordered. And like I said, our gas is going to be much, much more disordered than our liquid. But all of this has, as we increase our temperature, we are increasing our entropy. So this is showing a direct relationship between our temperature and our entropy. Even if it doesn't go through a phase change, right? Even within the phase, we are seeing, right, a sloped line, right? It's going up and to the right, which is telling us that we are increasing our entropy as we are increasing temperature. So when our materials change state, like we saw in the previous slide, right, when we went from solid to liquid to gas, the number of macrostates and microstates that it can have changes as well, right? So remember, macrostates is going to be the energetically equivalent ways that these molecules can be arranged, right? And so if you think about the solid, right, they're kind of locked into place, and so they're not going to have that many macrostates. But as we go to a liquid where they have more freedom of motion, they can move about more, and we have more macrostates associated with a liquid. And then a gas isn't constrained by that same, volume limitation really, so we're going to have a greater number of macrostates. So as we increase the number of macrostates, we are increasing the amount of entropy. Okay, and so that's just what this slide is talking about here. So heat flow, right, like we were just talking about, is going to be related to entropy. Okay, when we have some ice and we place it in water, our direction of heat flow is always going to be from the warmer temperature, right, the warmer substance, to the cooler substance. Heat always flows from hot to cold. It doesn't go the other way around. And we know this from the second law of thermodynamics, and we talked about this when we studied chapter 6 in Chem 1. We said heat is always going to flow from the hotter substance to the colder substance. But we didn't really talk about why that is. And in this class, we now know that the reason that it's going to flow from the hotter substance to the colder substance is because the dispersal of heat. We are looking for a large dispersal of heat. That will cause it to have greater entropy, and that will cause the entropy of the universe to increase. So our heat is always going to try and disperse across our entire system. All right, let's go ahead and get some practice on this. So here are some problems, and I want you to figure out or predict whether delta S of our system is going to be positive or negative for each of the following. So remember, our delta S of our system, our entropy, is going to increase, and that will be positive for something that is spontaneous, right? That kind of happens on its own. And it will be negative for something that wouldn't. Okay, so go ahead, pause here, see if you can predict why, or whether it will be positive or negative, and why it will be positive or negative. All right, let's go through this. So a hot beaker burning your fingers. This will be an increase in entropy because our heat is trying to disperse into our fingers, which is great, right? But that is going to increase our entropy. So remember, we're trying to increase the disorder of the universe. So as we do that, the heat will try to disperse throughout a system. So that's what's happening here. Water vapor condensing, that is going to be a negative change in entropy because we're going from a gas, which is very, very random, to a liquid, which is pretty ordered. So that will be a negative delta S. Separation of oil and vinegar in salad dressing, that is our system becoming more ordered. So that will be a negative delta S because we're separating the layers back out rather than having them combined as a mixture, which would be more random. Dissolving sugar in tea would be a positive delta S because our ions will now become hydrated into, our molecules become hydrated into our tea, and that will break up the crystal structure. The next one, we're looking at numbers of gas molecules. Okay, one of the slides earlier said total numbers of molecules, and that will be true for things like, if it goes from a solid and a liquid to maybe a solid and two liquids or something like that, right? But if we have gases, then we're just going to look at the total number of gas molecules on each side because gases have so much more entropy than solids and liquids. Okay, so you can think of like the entropy contribution of our solids and our liquids to be essentially negligible when we have gases present. So here we are forming a gas on our product side, so our delta S is going to be positive. In the next one, we have all gas molecules, and we're going from 2 gas molecules on the left to 1 plus 3 gives us 4 gas molecules on the right, so we are having a positive change in entropy. And then our last one, we are having our silver ion and our chloride ion come and form our silver chloride precipitate. That is becoming more ordered. We are pulling ions out of solution and forming a crystal, so that is going to be a negative delta S. Okay, let's talk about phase changes. So we know that entropy changes during a phase change. If you'll recall the graph from earlier, right, it looked like, the solid looked like this, and then we had our phase change, and then we had our liquid and our phase change and our gas, right? So we know that we are getting a very large increase in entropy during a phase change. And we can actually calculate that change in entropy that happens during those changes. If you'll recall from chapter 11 that we looked at in Chem 1, we know that a phase change is always going to be accompanied by an exchange of heat between the system and the surroundings. And so we use these delta H values. Okay, so the change in enthalpy values. So we had delta H vape, right, would be one of them. And so that would be the heat of vaporization, right? That would be whether it's, vaporizing or condensing. And then we have another one for melting and freezing, okay? But they're both going to be these delta H values. And delta H, remember, is usually in kilojoules per mole, and we can relate this to Q. Q is typically going to be in joules or kilojoules. Okay, so we can use this Q value from these phase changes into an equation for our change in entropy. And this is only going to be for reversible systems. And essentially, it's only going to be for phase changes because these are going to be reversible systems that are happening at a constant temperature and typically a constant pressure, okay? But the constant temperature is the part that's important here because our temperature is not changing on the bottom. So our change in entropy is going to occur when a reversible system exchanges a quantity of heat with its surroundings at a constant temperature. This is essentially the definition of a phase change. Okay, we're not having a change in temperature, so let's think like ice melting, right? When ice gets to 0, it will begin to melt. And until it all completely melts, that temperature will remain at 0. Once all of the ice is melted, then the temperature can begin to increase, but it can't increase until all of the ice is melted into water. Okay, so that's our constant temperature there during a phase change. And it took some heat, right? We had to input heat in order to cause our ice to melt. So we can calculate the amount of heat, we can take our amount of heat that it took for the ice to melt over our temperature, which would be 0, but this is going to be in Kelvin, so that would be 273. And then we could calculate our change in enthalpy our change in entropy associated with this phase change. Okay, but again, this is pretty much only going to be for phase changes because other changes are always going to be subject to that heat tax, right? Some of our work will be lost as heat. Here, we're not having any heat being lost as work, so we can do this calculation. So let's go ahead and try this out. So this says calculate the change in entropy that occurs in a system when 25 grams of water condenses from a gas to a liquid at the normal boiling point of water, which we know is 100 degrees Celsius. And just as a reminder, when it says the normal boiling point, that means the boiling point at 1 atm. Okay? And there's our delta H of vaporization. So we're going to go ahead and calculate the change in entropy. So we know our change in entropy is delta S over our reversible Q over T. So we don't have Q, right? And so this is what I was kind of talking about a little bit earlier. We don't have Q, but Q is related to our delta H value. Our delta H value is in kilojoules per mole, and that's the key here, this per mole, right? And we have 25 grams of water. So we can use our 25 grams of water to, convert that into moles, and then we can use this delta H value as a conversion factor to change into joules. Okay, so let's go ahead and go through this. So we have our 25 grams of water, and we're going to convert our 25 grams of water into moles of water using the molar mass. And then we can use our delta H value to convert our moles into kilojoules. Okay, and I want you to note here, this is a negative value because when we are condensing from a gas to a liquid, we are losing heat. That is an exothermic process because we are cooling our substance down. So make sure to pay attention, especially in this chapter, to the signs on things, right? As we've noticed, right, delta S is going to be positive when we're experiencing an increase in entropy, and negative when we are experiencing a decrease. When we have delta H, right, negative means it's exothermic and positive means it's endothermic, right? So we need to make sure to pay attention and don't drop any negatives here. So we have a negative for our delta H value because this is an exothermic process. And then we can go ahead and convert our kilojoules into joules. The reason that we are converting kilojoules into joules here is that our units for delta S are going to be joules per Kelvin, okay? Typically, just as a brief digression, typically our delta H values, our enthalpy values, are going to be in kilojoules per mole. And a little bit later in this chapter, we are going to get into delta G values, and those are also going to be in kilojoules per mole. But delta S is typically in joules per Kelvin. Okay, and so I'm pointing this out because it's really easy to forget that delta S is in joules, and you'll forget to convert it when we start interchanging all of these variables. Okay, so make yourself a note. Delta S is in joules per Kelvin. All right, so now that we have joules, we've kept our negative there. We can go ahead and plug it into this equation. So we have delta S is equal to our reversible Q over T, and make sure you change that T to Kelvin. Okay, and so there you go. There's your answer. I want you to go, sorry, I thought I had another practice problem there. Never mind. Let's move on. So the second law of thermodynamics says that the sign of delta S for a reaction doesn't predict the direction of a spontaneous reaction by itself. It contributes to it, right? Oftentimes, if we are having an increase in our entropy, then oftentimes that will be a spontaneous reaction, but that's not the only thing that goes into it, right? We've also looked at previously that enthalpy also plays a factor, right? Whether our process is exothermic or endothermic. So we need to take both of those into account. But so the way that this plays out is that we are going to look at the entropy of the universe. So a spontaneous process has to increase the entropy of the universe. So that will be the system and the surroundings together have to be greater than 0. They can be equal to 0 for a reversible process, but they have to be greater than 0 for a spontaneous process to occur. Okay, so if we have, say we have a decrease in the entropy of our system, okay, but it's still spontaneous, right? So if we have a decrease in the entropy of our system, that means that this must be offset by a really large increase in the entropy of our surroundings in order to still make the entropy of our universe increase. Okay, if it's spontaneous. So if we have a little tiny, if we have a decrease in the entropy of our system, that must be offset by a really large increase in the entropy of our surroundings in order to make this still be positive. Okay, so if our entropy is negative for our system, has to be really positive for our surroundings in order to make our, it's still positive for the change in the entropy of the universe. And that is what we are looking for it to be spontaneous. So things can still have a negative delta S value, right, and be spontaneous, but it just, something else has to be going on. So the thing that has to be going on is that the process has to be exothermic. If our process is exothermic, then it's going to add heat to the surroundings. And if it adds heat to the surroundings, right, we looked at that relationship between temperature and entropy earlier. So if it adds heat to the surroundings, it's making the surroundings more disordered. So even though our system is becoming more ordered, it's releasing a large amount of heat, which is causing the surroundings to become really disordered. So together, we're still having a net increase in disorder. Okay. If your system was endothermic, though, then we would have the opposite problem, right? We would take heat from the surroundings, which would decrease the entropy of the surroundings, and we can't have a decrease in the entropy of our system and a decrease in the entropy of our surroundings, because that will cause a decrease in the entropy of the universe. That will not be spontaneous. You can still make it happen, right? You would just have to continually input energy to make it happen. So this last little bit is that the amount of entropy that the surroundings change depend on the original temperature that they started at. So if we have something that's really cold and an exothermic reaction happens, then it's going to have a large increase in heat compared to where it started, and it will experience a larger increase in entropy because of that. If we have something that's already hot and then we have, more heat being added to it, it's not as big of a change, and it's going to experience a smaller increase in entropy. Okay, and the reason for this is that our units of entropy are joules per Kelvin. So if we are having, a smaller Kelvin down here on the bottom, then we're going to experience a larger, joule change. Or if we have a larger Kelvin on the bottom, then we'll have a smaller joule change, right? So the fact that it's directly related to that temperature is the reason we're having that the change in entropy is related to the initial temperature. So let's go ahead and look at this. Let's look at this using water as our example. Okay, at low temperatures, water will freeze, right? We can have water that will freeze below zero, and that is going from, a liquid, which is really disordered, to a solid, which is really ordered. So our entropy of our system is going to decrease, but we know that freezing is an exothermic process, right? Where our molecules are losing heat, they're cooling down. So that release of energy is going to our surroundings. And so when we have that release of energy, that is causing our surroundings to become more disordered because they are increasing in energy, right? So when we're below zero, right, or at zero, below zero, that means that our decrease in our entropy of our system, right, our liquid going to a solid, is offset by our increase in our entropy of the surroundings, the release of heat when that substance is cooling down. Okay, so that still has an overall positive delta S of our universe because the increase in the entropy of the surroundings was enough to offset the decrease in the entropy of our system. But if we think about it at 100 degrees Celsius, we're still having the same, right? This hasn't changed, right? We're still needing to order our system. We're going from a liquid to a solid. But since we're starting at a higher temperature, the release of heat at 100 degrees Celsius is not going to make as big an impact on the change in entropy of the surroundings because they're already hot. So when we add, heat to our already hot surroundings, we're not getting as big of a change, not as big of an impact. So here, our delta S of our surroundings is smaller because we're starting at a hotter temperature. And so it wasn't enough to offset the delta S of the universe, and the delta S of the universe would still be negative. So this is why water will freeze at 0 degrees Celsius, but it won't freeze at 100 because of this whole, delta S is going to be dependent on, or that change in delta S is going to be dependent on the temperature that we're starting at. All right, to sum all this up, the second law of thermodynamics demands that the entropy of the universe increase for a spontaneous process. So we can make that happen a lot of ways, right? We've talked about them. But processes like water vapor condensing are spontaneous, even though water vapor is more random than liquid water, right? We're going from gas to a liquid, but it can still happen. It can still be spontaneous because that entropy change, right, in the surroundings is large and compared to the entropy change in our system. And we are getting such a large increase in our entropy change in our surroundings that it still causes an increase in the entropy of the universe. Okay, and the reason that happens is because these processes are exothermic. Okay, so to sum up all of this, if we are going to have a decrease in the entropy of our system, then that decrease in the entropy of our system needs to be associated with an exothermic process so that it can release enough heat so that it can, go to the surroundings so that surroundings can become really disordered so that we can still have a net increase in disorder when we add our system and our surroundings together so that we still increase the entropy of the universe. Okay, so now let's go back to math a little bit. So the entropy change in the surroundings is going to be proportional to the amount of heat gained or lost by our system. So if our system is losing heat, right, we have a negative Q, then our surroundings are gaining heat, that is going to be a positive Q. And they're directly related, right? We're going to assume this is a closed system, so all of the energy that's being lost by our system is going to be gained by our surroundings. And like we've been talking about, the entropy change is in the surroundings is also inversely proportional to its temperature. We've talked about that quite a bit. And at constant pressure and temperature, then we can make a relationship like this. Okay, our change in entropy of our surroundings is going to be equal to the negative delta H of our system over T. So this is similar to the equation that we were just using, but that was only for reversible processes. This will be for any process as long as they are at constant pressure and constant temperature. So let's go ahead and give this a go. So this says calculate the entropy change of the surroundings at 25 degrees Celsius for the reaction below. So we have our delta H value. We know it's at 25 degrees Celsius, so we can go ahead and use that equation given. So here we are. So there's our equation. Our change in entropy of the surroundings is going to equal our change in enthalpy of the system over T. So we can plug things in, make sure, again, to keep track of your signs. So this was already negative. So when we have a negative here, you need to carry it through, which is going to end up making it positive. We need to always make sure that our temperatures are in Kelvin, okay? And then you can just divide that up. And then again, make sure we convert things to joules per Kelvin because this is change in entropy, not enthalpy or Gibbs free energy. And then I would always check, make sure it makes sense, right? We have a positive delta S here. Okay, so let's go ahead, let's look at our reaction, right? This is a combustion reaction. We have a hydrocarbon reacting with oxygen gas to produce carbon dioxide and water. We know that combustion reactions are really exothermic, right? Look at that, really exothermic, and they are spontaneous, right? They, burn up kind of by themselves. So the entropy of the surroundings should increase significantly because we are giving a lot of heat to the surroundings, right? That's really, really a lot of heat that's being released to the surroundings. Therefore, the entropy of the surroundings should increase, which is what we are seeing here. All right, let's try another one. So here we have the reaction below. Now we have an endothermic reaction, 66.4 kilojoules. So we want to calculate delta S of the surroundings, figure out the sign of delta S of the system, and then figure out whether the process is going to be spontaneous or not. So calculating delta S of the surroundings, we're going to do that just the way we did before using that equation. So we're going to plug in our delta H values. We're going to convert T to Kelvin. We'll divide those up, and then we'll change it into joules per Kelvin. So we have our sign of our delta S of the surroundings is going to be negative, okay? So this is not favorable. And that makes sense. We have a positive delta H value here. This is endothermic. That's typically going to be associated with a negative delta S of our surroundings because we are not releasing energy to our surroundings. We are absorbing energy from it, which is causing our surroundings, right, to lose energy so they become more ordered. So now we need to figure out the sign of delta S of our system. So when we look at it, we have 3 gas molecules here on the left, right? 2 plus 1. And then we only have 2 gas molecules here on the right. So since we're having fewer gas product molecules, delta S of the system is going to be negative. So we have a negative delta S of our surroundings, a negative delta S of our system. So this is going to be not spontaneous whatsoever. If we think about those graphs we were having before, right? Delta S of our system is negative. Delta S of our surroundings is negative. So our delta S of our universe is definitely negative. So it's going to be non-spontaneous. All right. Now let's talk about the third law of thermodynamics. So we have this thing called absolute entropy. And the absolute entropy of a substance is the amount of energy that it has due to dispersion of the energy through its particles, right? We know that particles are vibrating in place. Even in a solid, right, they're always moving. They're vibrating ever so slightly. But if we had a perfect crystal that had exactly perfect alignment of all of the particles, and then we cooled it down to absolute zero, right, which would be 0 Kelvin, then the particles will have minimum energy, right? The smallest amount of energy possible. So there would only be one microstate because they can't move anywhere else. Okay, so the third law states that the entropy of a perfect crystal at 0 Kelvin is 0. So we have a 0 point essentially for our entropy. Anything that is at a temperature above that or has a crystal structure that's not perfect is going to have some amount of entropy. Okay, so the absolute entropy of any substance other than this perfect crystal at 0 Kelvin is always going to be positive because they always have some amount of disorder compared to this perfect crystal. So we call these entropies that are associated with our substances, we call them standard molar entropies, and their sign is going to be S0. This is an extensive property, so it depends on how much of it you have. Okay, the standard molar entropy values are going to be for 1 mole of a substance, and it's always going to be at 298 Kelvin, which is 25 degrees Celsius, and it's going to be for a particular state, for a particular allotrope, which is a way that the molecules are arranged, particular molecular complexity, a particular molar mass, a particular degree of dissolution, right? But we have these specific values that are going to be associated with very specific configurations of our molecules at exactly 298 Kelvin for 1 mole of the substance. Usually the way this is going to play out is that it's going to be at 1 atmosphere for gases, 1 molar for solutions, and we said, 1 mole for substances, and it's going to be the substance in its most stable form for solids and liquids. So here you are. So here's a bunch of standard molar entropy values. As you can see, they are all positive and they are all not 0, right? Because none of these are going to be perfect crystals, and these aren't at 0 Kelvin anyways. These are at 298 Kelvin, so it won't be 0. So they all have some amount of entropy compared to that perfect crystal. We'll talk about how these are related as we move forward, but I do want you to know that you're not responsible for memorizing any of these. I will always give you these values so that you can use them. So let's compare these. So the gas state of anything is always going to have more entropy than the liquid state at a given temperature. We know that, right? Gases are more disordered than liquids, so it makes sense that they have a higher entropy value. Similarly, the liquid state is going to have a larger entropy than a solid state at a particular temperature. And this is for, a specific molecule. So here this would be for like water as a liquid or water as a gas. When we are comparing similar molecules, and so here we have noble gases, we can look at the molar mass if they are similar. So the larger the molar mass, the larger the entropy. And the reason for this is that heavier atoms are closer to each other, and so they allow for more dispersal of the energy through their states. So they are going to have more entropy. When we have different allotropes, we will have different entropies, and allotropes are just in ways, like this is a really good example, carbon. Carbon is like if we have like diamond or graphite, right, it's just going to be a bunch of carbon all bonded together through these covalent bonds. Carbon forms a lot of really cool structures because it can make those 4 bonds, and so it can bond to itself in really neat ways. So when we have a diamond, you can see that it's forming a really cool crystal pattern, which is what gives it its clarity. But graphite forms in sheets. So as you can see, like this is a layer, and this is a layer, and this is a layer. Okay, and the layers don't interact with each other. Whereas in the crystal, right, they're all kind of interbonded, interconnected. Okay, so the more constrained we have these allotropes, the lower their entropy because they don't have as much freedom of movement. So graphite is not as confined because those carbon molecules or those carbon atoms are not bonded to each other between the sheets, so it can move about more. I mean, still not a lot, right? We have pretty low entropies, but more than it could as the diamond because it's not bonded. All right, so when we look at larger molecules or more complex molecules, we are going to have an increase in the amount of standard molar entropy. Okay, so as we get a larger molecule, they can have more available energy states. They can move more, right? We have more translational motion, which means side to side. They can rotate, they can vibrate in and out, right? The bonds are not stagnant. They can actually get closer to each other and farther away. But as we get more and more complex states, they have more of these microstates and macrostates, and so they can have more dispersal of energy through the states, which gives them a higher molar entropy value. So here, same kind of thing. If we have a more complex molecule, we are going to have a higher standard molar entropy. And then, like we've talked about before, if we dissolve our solid, right? So here we have a solid, here we have an aqueous solution. As we dissolve it, it's going to become more disordered, and it will have a higher standard molar entropy. All right, I want you to go through these and predict which of them, right, which thing in the pair will have a higher entropy. And then I want you to explain why you picked that one. So go ahead, pause here, see if you can figure out the answers, and come back when you're ready. All right, let's go over this. So in this first one, right, we have our 1 mole of SO3 will have a greater entropy because there are more atoms in our molecule, right? We have a more complex molecule. There are more ways that it can be arranged, and it can disperse its energy more, so we have a greater standard molar entropy. Here, a gas is always going to be more disordered than a solid because it has more freedom of motion. This one, we have a greater number of molecules, right? 3 versus 2. We have a dissolved solid that is always going to have more freedom of motion than our crystal. At higher temperatures, we have higher entropy, right? Entropy increases with temperature. And then for the last one, as we get, as we have similar structures, right? CF4 and CCl4, both of those are tetrahedral molecules, so they have the same structure. So if they have the same structure or the similar structure, then our entropy is going to increase with molar mass. And just a reminder, just in general, particles with more freedom of motion have more microstates, and they will be able to better disperse their kinetic energy, which means that they have higher entropy. So this would be, if we raise the temperature or we have more particles, then that is going to increase our entropy. All right, our last topic for today is the standard entropy change. Okay, the standard entropy change is the difference in the absolute entropy between the reactants and products under standard conditions. Okay, so this will be at 25 degrees Celsius. And so we will be able to calculate our standard enthalpy of our reaction, standard entropy of our reaction by doing products minus reactants is essentially how this is going to play out. So this is the Greek letter sigma. This means sum up. So we are going to add up the coefficients of our products times their standard molar entropy values, and then subtract the sum of the coefficients of our reactants times their standard molar entropy values. Okay, and this is just a reminder, when you do this, we've done calculations like this before. We did this in Chem 1, and we did this with delta H values. And when we did this with our standard enthalpy values, those delta H's of formation, for an element, it was always 0 because we don't need to form our element, right? Elements just exist. But the absolute entropy of things are not 0, right? Elements do not have a 0 entropy. Remember, the only thing that's got that 0 entropy would be a perfect crystal at 0 Kelvin. So everything is going to have an entropy value because it's not going to be at 0 Kelvin. It will have some amount of disorder. So make sure you're not putting 0 for pure elements. So when we do this, the reason that we are multiplying by these coefficients is that entropy is an extensive property. So it's a function of the number of moles of our stuff, right? And so we need to multiply our entropy values by the number of moles of our, our products or our reactants in the balanced chemical equation. And then remember, generally just the more complex that molecule is, the higher the standard entropy value. And this will always be a good check to make sure you're looking at the right compounds. If something is really low and it looks like a complex molecule, you may have picked the wrong value. All right, so this is how they'll show up. You'll always have a table and you're going to pull the values from there. Typically, when you're doing, worksheets and things like that, it'll either be in the back of your book or at the end of a worksheet, or on ALEX, there's a little button you can click and it will give you the standard molar entropy values and the enthalpy values and the Gibbs free energy values. It's all under thermodynamics data. Okay, so here we go. Calculate the standard molar entropy for the reaction, and there it is. So we are going to use that equation that we just had, where we're going to do products minus reactants. So here we go. So we take our products, right? So we're going to go 4 times our value for nitrogen monoxide, plus 6 times our value for water. Okay, and then we put all of that in brackets, and then we're going to subtract our reactants. So 4 times our value for ammonia, plus 5 times our value for oxygen. And again, remember, this is not 0 because this is not an enthalpy of formation. So we can go ahead and plug in the values from the table, and then you can calculate your answer. It's pretty straightforward. We've done calculations like this before, so this should be familiar and hopefully easy. Always check though at the end to make sure that your answer makes sense. So here we have a positive delta S value, and if we look at our reaction, we have 9 moles of gas going to 10 moles of gas. So this is good, right? We would expect that our delta S value would be positive, and in fact it is, which is great. All right, you go ahead and try one, just to make sure you've got this down before you go off and try it on your own. This is exactly the same, or essentially the same as the one we just did. Again, products minus reactants, and then come back when you're ready. All right, let's go over this. So again, we're going to use that formula just like we did before, and then we're going to do products minus reactants. So we have 2 times our value for water minus 2 times our value for hydrogen plus our value for oxygen, which again, remember, is not 0. And then we'll plug in those values and we will get a negative delta S value. And again, double check, does that make sense? We're going from 3 moles of gas to 2 moles of gas. So we are decreasing the entropy of our system. So that makes sense. We are getting a negative entropy value. And that's it for today. We covered a lot of ground. We talked a lot about changes in entropy. That was kind of the theme of today. And we've started introducing how to do some calculations related to these changes in entropy. So go ahead, start working on that Chapter 18 lecture worksheet packet so that you can get some practice with these equations and with doing, with identifying, which things will have greater entropy and when you will see an increase or a decrease in entropy. So keep working hard, read your textbook, and ask me if you have any questions. As always, keep working hard, and I will talk to you guys next time.